IT 361 Module 5 Part 1. In this part we are going to discuss about planar graphs. A graph G is said to be planar if there exists some geometric representation of the graph G which can be drawn on a plane such that no two of its edges intersect. A graph that cannot be drawn on a plane without a crossover between its edges is called non-planar. A drawing of a geometric representation of a graph on any surface is that no edges intersect is called embedding. A geometric graph G is planar if there exists a graph isomorphic to G that is embedded in a plane. Otherwise, G is non-planar. An embedding of a planar graph G on a plane is called a plane representation of G. These are some of the examples of planar graphs in which you can see none of the edges in each of the graphs are intersecting. So that is why these graphs are called planar graphs. Particularly, these are the planar embeddings or the plane embeddings of the corresponding graphs. These are some of the examples of non-planar graphs. The first one is K5, which is a complete graph with 5 vertices, and the second one is K33, which is a complete bipartite graph with 6 vertices. Both these graphs are non-planar graphs, and these graphs are also known as Kuratowski's graphs. A complete graph with 5 vertices is the first of the 2 graphs of Kuratowski K5. The second graph of Kuratowski is a regular connected graph with 6 vertices and 9 edges, shown in its 2 common geometric representations in the figures. And K33, where it is fairly easy to see that the graphs are isomorphic. Now, there is a theorem that Kuratowski's second graph, which is also called as K33, is also non-planar. That is, the 2 graphs of Kuratowski's are K5 and K33, both are non-planar. These are properties common to the 2 graphs of Kuratowski. That is, one of the properties is that both are non-planar graphs, another one is that both are regular graphs. The figure given on the left side is a planar graph, and in the right side of that you can see the planar representation of the given graph. The third property of the Kuratowski's graph is that if we are removing one edge or vertex from the corresponding K5 or K33, then it will become a planar graph. Here you can see the step-by-step procedure of the construction of K5. If you are observing the corresponding graphs, in the first 4 graphs you can see all the 4 steps. In all the 4 steps, the graph is actually planar. But in the last step, namely the subdivision E, the graph over there is non-planar by the addition of the last edge. Okay, that's why we are saying that in K5, if we are removing one edge or one vertex from the complete graph K5, you will get it as a planar graph. The fourth property of Kuratowski's graphs is that Kuratowski's first graph, namely K5, is a non-planar graph with the smallest number of vertices, and Kuratowski's second graph, namely K33, is a non-planar graph with the smallest number of edges. Thus, both are the simplest non-planar graphs. Now we are going to see different representations of a planar graph. The first we can see about what is a region. A plane representation of a graph divides a plane into regions, also called as windows, faces or meshes, and that is shown in the figure just after this one. A region is characterized by the set of edges or the set of vertices forming its boundary. Note that a region is not defined in a non-planar graph or even in a planar graph not embedded in a plane. Now in this figure 4.9 actually gives the representations of K5, K33, particularly the Kuratowski's second graph. In figure 4.10, you can see the finite regions representing the which is noted here by the digits 1, 2, 3, 4 and 5. All these are the finite regions and the number stands for the regions. Next is about infinite region. The portion of the plane lying outside a graph embedded in a plane such as region which is not shaded in the above figure is infinite in its extent. Such a region is called the infinite unbounded outer or exterior region for that particular plane representation. Like other regions, the infinite region is also characterized by a set of edges or vertices. Clearly, by changing the embedding of a given planar graph, we can change the infinite region. Next is the embedding on a sphere. To eliminate the distinction between finite and infinite regions, a planar graph is often embedded in the surface of a sphere. It is accomplished by stereographic projection of a sphere on a plane. Put the sphere on the plane and call the point of contact SP, namely South Pole. At point SP, draw a straight line perpendicular to the plane and let the point where this line intersects the surface of the sphere be called NP, namely North Pole. Now, corresponding to any point P on the plane, there exists a unique point P' on the sphere and vice versa, where P' is a point at which a straight line from point P to point NP intersects the surface of the sphere. Thus, there is a one-to-one correspondence between the points of the sphere and the finite points on the plane, and points at infinity in the plane correspond to the point NP on the sphere. Next is a theorem which states that a graph can be embedded in the surface of a sphere if and only if it can be embedded in a plane. A planar graph embedded in the surface of a sphere divides the surface into different regions. Each region on the sphere is finite, the infinite region on the plane having been mapped onto the region containing the point NP. Now it is clear that by suitably rotating the sphere, we can make any specified region map onto the infinite region on the plane. From this we obtain actually the Euler's theorem. And the Euler's theorem states that a connected planar graph with n vertices and e edges has e minus n plus 2 regions. Let's see how we can prove it. So the proof is actually by the method of mathematical induction on the number of edges of the graph G. We will start by e equal to 0. So if e equal to 0, then n equal to 1 since it is connected. And the number of regions, since it is an infinite region, say R is, and the number of regions is only a single one, which is actually the infinite region. Thus, R is equal to 1 here. The theorem is true for this case, so it is holding over here, because if you are substituting e equal to 0, n equal to 1 and this R, number of regions as equal to 1, on substituting it as e minus n plus 2, you will get it as 1 minus 1 plus 2, which is equal to the number of regions present over here. So e is actually 0 over here, n is 1 over here. So if e equal to 0 and n equal to 1, you will get the theorem holding over here. Okay. So next, as in the case of the procedure of mathematical induction, now we assume that the theorem holds for at most e minus 1 edges and let G be a plane with e edges. If G is a tree, then e equal to n minus 1 and R equal to n minus 1 minus n plus 2 equal to 1 as required. If G is not a tree, then X can be X be an edge in some cycle of G, then G minus E is a connected plane with n vertices, E minus 1 edges and R minus 1 edges, so that E minus 1 minus n plus 2 equal to R minus 1 by the induction hypothesis. It follows that E minus n plus 2 equal to R as it is required. Next is a corollary for the Euler's formula. It says that in any simple connected planar graph with f regions, n vertices and e edges, specifically e greater than 2, that is specifically in the case of number of edges greater than 2, the following inequalities must hold: e greater than or equal to 2f by 3, e greater than or equal to 3n minus 6. Let's see how we can prove this one. Since each region is bounded by at least 3 edges and each edge belongs to exactly 2 2 of the regions, we can write 2e greater than or equal to 3f. From here we will get e greater than or equal to 3 by 2f. And if you are substituting this inequality in the Euler's theorem, we can derive, we will get e greater than or equal to 3 by 2 into e minus n plus 2, from which we will get it simplified as e less than or equal to 3n minus 6. So that's all from the topic of planar graphs. Thank you.